Welcome you all to the session on introduction about our Verilog code. Verilog. Verilog is an hardware description language. In short form, it is referred as an SJCE. What is the main purpose of this SJCE? It is used to design, model and simulate electronic digital systems. This electronic digital systems is a combination of combination circuits and sequential circuits. This combination circuits are collection of the gates and it doesn't have any memory and the output depends only on the present input. Whereas the sequential circuits or a memory elements, the output depends on the previous input. So the examples are the flip-flops. So these two are the basic components of our electronic digital systems. Okay. What is the role of this SJCE? It is going to describe how these components are interconnected. What are the inputs? What are its outputs? All these will be described in this hardware description language. This Verilog coding can be written in three different ways. One is a structural or gate level model. Another one is data flow modeling. And the third one is behavioral modeling. The structural and the data flow model is used for design our combination circuits, to describe the combination circuits, whereas the behavioral model and the data flow model, these two are together used to describe our sequential circuits. From the name itself we can refer the structural or gate. So the name of the gates will be explicitly described in the coding. And this data flow indicates how the input values are getting propagated to the output. And this is behavioral model. From the truth table itself we can write the coding. So among these three, there is no standard rules or conditions whether we have to follow structural or behavioral data flow or behavioral. The combination of this can also be used. In this Verilog coding, in this session, we will discuss about the Verilog code for ripple carry adder. As I told you earlier, ripple carry adder is a combination of or a collection of full adders based on the number of bits it is required. If it is an 8-bit ripple carry adder, it will have the combination of 8 full adders. 5-bit ripple carry adder means it will have a 5 full adders. Okay. Now full adder. What is full adder? It is going to add 2 input bits and the carry generated in the previous stage. So that is referred as full adder. If I assume A and B are the 2 input bits and the C in is the carry generated in the previous stage. So as we consider the 3 input bits, definitely we will have 8 combinations. So when you add in a binary addition, 0 plus 0 is 0 and 0 plus 1 is 1. When you add 2 1 bits, the answer is going to be 2. So what is the binary equivalence of 1 0? In that case, 0 is an sum and 1 is a carry. So when I consider this case, 0 1 1 1, the sum is going to be 0 and the carry is 1. When you consider this triple one, this is going to be a 3, and what is the binary equivalent for 3? This is 1 1. Either this 1 is a sum and the other one is a carry. So when I am going to describe this full adder as a circuit, what are the gates involved in it? So to find out it, I am going to express this as an equation. This equation can be derived using a Karnaugh map in the simplified form. So how will you create this Karnaugh map? Wherever you have 1 in this truth table, that will be tabulated in the Karnaugh map. By applying this simplification rule, I have got the sum equation as A XOR B C, whereas when I consider the values of 1 in the carry and when I tabulating it in the gamma, it gives the answer AB plus BC plus AC. From these expressions, we have identified that to implement the sum, I need 2 XOR. To implement the carry, I need 3 this logical OR gate is required as well as a logical AND gate is required. So to represent this, I am going for this second. So what are the inputs? A, B, C in all the inputs. What are my outputs? Sum and carry of the outputs. So to represent this, A and B are first XOR and that will be XOR with the third input bit and so on. So this is the construction of our full adder circuit. Okay. In the Verilog code, how we are going to describe this hardware, that we will see now. So this is our circuit. So for assumption, I have taken this X, Y, Z are the inputs. Okay. So in that, so whatever is described in this blue color is indicating the fundamental blocks or the keywords, sorry not blocks, it is the keywords used in the Verilog code words. In that, the very important thing is a module. Module is indicating, it is describing the functional unit of the circuit and what are its inputs, it is a list of inputs and what are its outputs. And within this body of the module, you will have the functional description about the circuit. Okay. So, from this, what are the inputs? X, Y, Z are the inputs. That is referred by the keyword input. And then sum and carry, S and C not are my outputs. So that is described by the keywords output. But intermediate, when you observe the circuit, we have some 3 intermediate results, T1, T2 and T3. These are not the final outputs. So that will be stored with the temporary variables. Apart from input and output, you have the temporary variables. These temporary variables are represented by the term called as a wire. Wire is a temporary variable. So in this equation, in this circuit, totally we require 3 intermediate values. So therefore, this wire T1, T2, T3. Okay. Now we will see that. As I told, this Verilog code can be written using 3 types of modeling. This coding has been written using a structured or gate level modeling. That means the description is explicitly representing the name of the gates. So XOR gate. Totally how many XOR gates are used? 2 XOR gates are used. Therefore XOR, and I naming those gates are G1 and G2. The first one G1. For this I am naming this is G1. For this G1, what are my inputs? X and Y are the inputs and the output is T1. Therefore I have taken this is my output and the X and Y are the inputs. For the second XOR gate, what is the final output? S is the output and the inputs are this T1 and the Z. Therefore T1, Z. Now when you are coming to the next one, AND gate I am going to use. How many AND gates we have used? 2 AND gates. Therefore let me name this is AND gate and already I have named this G1 and G2. Therefore G3 and G4 I have used. And what are the inputs for the gates G3? This is T1 and Z. T1 and Z it is going to give this one, this T3 and this is going to generate my T2. And after that, these temporary variables are added together to generate my final output, that is my carry. So these all are encapsulated within this module. This is our function unit. It is indicating the functional relationship between the inputs and the outputs and the gates equality. Everything is all described. So this module is indicating the functional relationship among the inputs and the outputs and what are the gates are involved in it and how these values are interconnected, how the values are propagated. All are clearly explained in this module and this is ending with the keyword end module. So this is a HDL or Verilog code for a full adder. But our objective is creating a triple carry adder. So let me take an example of 8-bit triple carry adder. That means totally I have 8 full adder circuits. 8 full adder circuits are there. So each full adder will have 2 input bits and it will generate 2 output bits, sum and carry. So let me explain. This is A0 to A7 and B0 to B7. These are my 2 inputs. If a that will also be an 8-bit number. So therefore sum of 0 to sum of 7 is there. And then carry. The carry is finally what is carry generated with the this one most significant bit. The intermediates will be carried and it is added in the next one. So you observe the cycle carry is. While adding on the lower 2 bits, there will not be any carry. Therefore, the C is taken as 0. And it is generating one carry and I am naming it as C of 0. That is forwarded here. Therefore, what are the inputs here? A1, B1 and the C of 0. So it produces an output sum of 1. And what is the carry associated with this? C of 1 is the carry. Likewise, the carry is propagated. And the carry propagated generated finally from the MSB adder. That is our final carry of the circuit. Okay. So let me explain the hardware description language. How we are applying this GDL. How we are writing the Verilog code for this ripple carry adder circuit. See, while explaining this, I am going to tell a very important thing called instantiation. Okay, now we will see how to write a Verilog code for a ripple carry adder. In this, the very important concept we have is an instantiation. What is meant by this instantiation? In the ripple carry adder circuit, we have a full adder. So to reduce the code and to reduce the space occupied by the code, we are going to use our instantiation. So what is meant by this? This is a full adder circuit. This is our SJCE language for our full adder circuit, and this is referred as one instance. This full adder is going to be used 8 times in our main circuit. These are not my circuit. Main program. So in the main program, this instance will be called 8 times. This process is referred as an instantiation. So this is known as an instance, and this instance will be called 8 times in the main program. So that is known as an instantiation. If it is on a 5-bit ripple carry adder, this will be called 5 times in the main program. So this is the concept of instantiation. Now we will see the code for it. The another important thumb rule is whatever the variables we used in the basic instance should not be repeated in the main program, main module. So in this full adder, in the basic module, I have taken x, y, z are my inputs and the s and c not my sum and carry. So in the main program, and one more thing, what is the name I have given here? It is a full adder. Now I have given a module ripple -8 adder. It is a nuisance friendly name. You can give any name for it. Here I have named it as a ripple -8 adder. And then ABC, some new input variable I have chosen, and the sum and carry of my outputs. And then in the basic full adder, this x, y, z are in 1 bit. Whereas in the ripple carry adder, it is going to be of an 8-bit wide. Therefore, I am naming it as I am declaring it as an array. Therefore, A is a variable 0 to 7. That is my array. Therefore, A0 to A7. My second input is B, and that is also of 8-bit wide. Therefore, 0 to 7. Whereas the carry in, it is going to be 1-bit only. Therefore, input C in alone. C is a variable I will use. So the input is a keyword. And then the output is also of 8 bits. Therefore, 0 to 7. And what is the name assigned to that sum? And then the another output is a carry and it is a 1-bit wide. Therefore, it is declared as such. And then in the full adder, in the circuit we have 3 intermediate variables T1, T2, T3. Whereas in the full adder, this ripple carry adder, at these stages you want to preserve the carry generated in the intermediate stages. Therefore, they are the temporary variables. So how will you store the temporary variables? By means of the term wire. And what is the length of it? Cn you need not to store, carry you need not to store. Therefore, in between you have 6 variables. Therefore, 7. Therefore, 0 to 6 I can use. Clear? Therefore, 0 to 6 and the name I have given is a C. Okay. Now, this process is known as an instantiation. What is the name I have used in the basic module full adder? The same name only here we have to use. If you change the name, then the program will not work. The same name, whatever you used it, the same name has to be replicated here. Okay. And then like our previously, when you use the two XOR gates, what we gave a name G1, G2 like this. Similarly, here I am going to use totally 8 times this full adder. Therefore, full adder FA1. When you consider this FA1, what are my inputs? A of 0 and B of 0 are input, and the C is an input. These three are my inputs. And what are my outputs? Sum of 0 and C of 0 are my output. There should not be any swapping between the input and output variables. Okay, and then full adder to A of 1, B of 1. And what is my third input? The C of 0, that is the output of the previous is given here, and the sum of 1 and C of 1 are going to be our output. So likewise, this 8 adder, this full adder is instantiated 8 times in this thing. So this is the end module. Therefore, in the main module, when you have a hierarchy design like this, so in the main module, this basic module can be called many times. So this is the program. Okay. Once the program is done, now this project has to be created. Okay, the project has to be created. So Xilinx is one of the platform we have. This Xilinx is an ISC, that is Integrated Simulation or Synthesis Environment. It has a provision for creating a project and writing a program. This is the test mode. It will be in the editor mode. This program will be typed, and it has a provision for compiling it and producing the simulation. Okay. So after doing the simulation, that is in the another video about the execution of this Verilog module using a Xilinx platform. Okay, the Xilinx is a platform used to create and this one execute the program. Okay. Now, what we see at the output of the Xilinx? The Xilinx will produce the two output inputs. So we will verify whether circuit is created correctly. That is referred as an RTL, Register Transfer Level. That I will explain in the next video. This is referred as an RTL, Register Transfer Level. So it describes what are the inputs are there and what are the outputs associated with it. So it is a high level abstraction level of the circuit. Within this, it looks like an IC, right? So within this IC, you will have all the circuits we used in the circuit. Okay. Once this is done. Now we want to verify whether the program written is working correctly for this logic. Whether if I give 2 zeros, whether it produces 0. When I give 2 ones, whether it is producing 1 0 like this, I want to check. Therefore, for that, the Xilinx have a provision that is referred as test bench waveform. That is a visual representation. Test bench waveform is a visual representation of the all possible inputs and output. This is the one sample test bench waveform for my ripple carry adder. So as I told you, so we have, so here it is a simulated output, and what is the name of this waveform? Test bench waveform. So these are the two inputs, 0 to 7, and then Cin, and these are my two outputs. Okay. Whereas in the Xilinx you have a cursor. So when you move the cursor and when you get the cursor in a particular point, the corresponding value will be displayed here. When my inputs is like this, and when the other input is this one, so when I add these two together, 1 plus 1 is 0, therefore 0 is here, and 1 is carry generated, therefore this 1 added here, and that is generated by carry, that is my output. So that is described in the this one sum output. Whereas in the carry, at the 8th full adder doesn't generate any carry, therefore the carry output is 0. So this is known as our test bench waveform. In that you can see that this is a 0 nanosecond, 200 nanosecond. These values you can zoom it and zoom up, and you can see the result in the Xilinx platform. In this session, we will discuss about the Verilog code of our 4-bit ALU. What is ALU? Arithmetic and logical unit. What this 4-bit indicates? All the operators are of 4-bit wide. So now we'll see how to create a code for this Verilog code. Okay. So let me explain. In this example, I am going to do 4 operations. Addition I am going to do, NAND I am going to do, I am going to do another comparison operation and one logical operation. This is my arithmetic, logical, this NAND and XOR are logical operation, and then this is greater is also applying a logic, and it is telling whether it is a greater or a number. It is only these 4 I have taken in this example. And then as it is a 4-bit ALU, my inputs are 4-bit wide, and the name of the module I have given is INP I have given. And then the width of my inputs are 0 to 3 and 0 to 3. Indicates it is a 4-bit wide. And then as I am going to represent, or I am going to perform only 4 operations. To represent each operation, I need one binary code as it has 4. 2-bit representation is sufficient to indicate this 4 combinations. Therefore, this input output, I am creating another variable called as an output, and it is of 2-bit wide. So as the operands are, as the inputs are 4-bit wide, the output is also going to be 4-bit wide. Where this comparison allowed, it is declared as a single-bit variable. Now again I am coming back to the module definition. So what are the inputs I have used? A and B are the input. Output is also I have used as an input to indicate a type of operation. And what are the outputs? Data is it and comparison. These two are an output. Those I have listed at the last. Okay. Now parameter. So when the value is 0, 0, it is indicating the addition operation. When it is 0, 1, that is it is indicating a NAND operation. Greater than, when it is 1, 0, I am going to perform a greater than operation. You are instructing the hardware to perform the function when the parameter value is like this. And then when the XOR operation is 3, when the parameter value is 3, it will perform an XOR operation. Okay. Now, I see that it is an assign. I am going to assign a value. Data is there. What is this one? See, this equal is like the previous thing. This equal is an assignment operator, where this double equal sign indicates the comparison operation. Therefore, I am comparing this output. What is this output? What is the parameter value? When the output value is equivalent to the parameter value, so add means 0 will be there. When the output is 0 and the parameter is 0, it is going to perform an addition operation. Okay. And then when the output is 1 and this parameter value is also 1, it is going to, so this is like addition operation. Okay. So NAND means this ampersand symbol indicates an AND operation, and this is indicating by negate. Okay. And then all the operations are delimited by the colon. Okay. And the third one is when the value is 3, it is going to perform our XOR operation. This is a symbol for XOR operation, and then when the output is equivalent, it is going to perform it. Okay. And then finally the comparison operation. See here, this comparison operation is taken as SJCE, assign output is equal to greater than. If it is so, A is greater than B, this operation will be done. It will be returning a true result. Okay. What is this tick? This will be representing Bx. Tick Bx. What does it indicate? It is indicating the value is a binary value. The tick H means that representation is going to be an hexadecimal value. Here we are representing all the values in the binary form. Therefore, it is represented B. Okay, this B is an operand and this B indicates the binary value. So in this way, this 4-bit ALU will be okay. In case you want to generate an 8-bit ALU with many combinations, I want to include the OR operation as well and the NOR operation. So many, whatever the combinations you want to perform, that can be incorporated. So where we will go and change? We will go and change in the output side. So instead of 4 combinations means 2 input bits are used. If I want to use 8 combinations, I will be going for 3-bit wide. 16 means 4-bit wide and vice versa. Similarly, if we want to generate one, if we want to create one 16-bit circle, 16-bit ALU we want to create, then this input bits will be 0 to 15 and so on. But the rest of the program and the combinations is going to be the same. Thank you. In this video, we are going to describe the universal shift register. Why this name is universal shift register? In the shift register, we have the options. The values can be shifted right or shifted left or rotate left or rotate right like that. That's what when all the 4 operations are being done using a single code, that's what I just refer as a universal shift register. Okay, and then we will see how we are writing the target description language, that is a Verilog code for this universal shift register. See here, this program, this Verilog has been written using our behavioral model, how the circuit has to behave to act as a universal shift register. So, here there is no need for instantiation and all. And then the behavioral model is explicitly seen using this case, always, if. These instructions are indicating the program has been written using our behavioral modeling. Okay. And what is the first keyword we will be using? Module is the first keyword, and automatically it will have an end module. That is by default. What is the need given here? Unique shift 8. Because what I mean, it is a 8-bit shift register. I am going to design an 8-bit shift register. So this is the name I have given to it. Okay. And then to shift the value. First of all, I want to have an input. Okay. So this is my basic input. And then I want to specify whether we want to carry out the shift left operation or right or rotate right or rotate left like that. Before like opcode, right? Opcode, here I am using one shift, rotate, left, single. So it is a user friendly. You can write out your own also, some new variable also you can give. And apart from this, you will have for an input, you will have an associated input. And clock and reset, these two takes a major role in the thing. Initially, and it is one of the sequential circuit, the flip-flops takes a major component in the circuit. So initially all the flip-flops have to be set to 0, reset to 0. And whenever I am giving reset, then values will be reset to 0. Therefore, we have another input called as a reset. Okay. And then based on the clock only, this it is going to all the flip-flops will changes its state. Okay. Now, what is the output? Here we have this register is also indicating it is going to store the value, and it is an 8-bit word, therefore 0 to 7. And then totally how many operations we are going to do? Shift left, shift right, rotate right, and rotate left. These are 4 works we want to do, 4 tasks we want to do. Therefore 2-bit combinations will work out forward. Therefore I am representing this, I am declaring this input as a 2-bit word, therefore 0 to 1. And then it is an 8-bit shift register. Therefore, the input is going to be 8-bit. It is declared as an array. And then to control the operation, we want to have both clock and reset. That is declared as this one. And then, once one operation is done, the values will be changed. Therefore, the input I want to retain one into temporary variable. I am naming that variable as a temp. And what is the type of that variable? It is a register. Therefore, 0 to 7 I will use. Okay. Now, I don't want to restrict this one, clock and reset. Where I want to do the change? I want to do the transition only at the positive edge of the clock and the positive edge of the reset. It is not a mandatory, it is our choice. Either we can go for positive edge or negative edge. But this always happens. So when that condition is satisfied, some group of instructions will be executed. Therefore, it is start with begin, and under this condition, it has to complete till this one. So, when this particular condition is satisfied, it has to start from begin and then here. Okay, you will see that. So, this is the reset. When the reset is there, what will happen to our output? All the 8 bits will be zeros. And then, see here, in the this one 8-bit H. What is H indicates? It is the hexadecimal representation. In the binary representation, you have 8 bits. Okay, and this 8 bits, when it is represented as hexadecimal, group of 4 bits. That is 1 number is taken as 1 digit. Okay, therefore, here we have only 2 digits, and this H indicates it's hexadecimal, and this 8 indicates the 8 bits are represented in hexadecimal form. Therefore, it is 2 digits. Everything is indicated here. And then, if it is not reset is not active, the actual operation will be carried out. This operation in the sense, shift right, shift left, or rotate left, if you want. Therefore, else, we want to do the operation. In that, first of all, we are storing our input to a temporary variable. With that, this is over. Only one operation we are doing, and then the key statement takes a major role here. This key statement gives 4 combinations. 0, 0, 0, 1, 1, 0, 1, 1. And this is a 2-bit. Totally 2 bits are there, and then tick D. B. This B means it is a binary value. So 0, 0, 0, these are the 4 binary values. Okay. Now, what is this operation indicates? When this operation value is given, see here, this one, this shift right value, that is going to be the value. So what should be my output? What should be my output? When this value, when this case value, this shift right is 0, 0, I need to do one left shift. When the value is 0, 1, this temporary variable, the input which I have stored in the temporary value will be shifted right. If it is 1, 0, so what is known as this rotate left? Rotate left, when you do with the rotate left, what will happen? The MSB bit will be wrapped around your LSB bit. Therefore, 0 to 6 comes to the upper higher position and the MSB bit is coming and wrapping around and coming to the 0th position. If it is of rotate right, so you are writing the, you are shifting it rightwards and this LSB bit will be moving to our MSB bit, shifting right. Therefore, the first position is coming to 0th position and so on. So 0 to 6, 1 to 7 is coming occupying the position of 0 to 6 and 0 to bit is now coming to this MSB bit. So this is a thing. If these two are not there, they will display the invalid shift control input. Okay, this case is ended with this AND case. Okay, now what this AND becomes? For one of this positive edge clock, all these operations will carry out. Therefore, this for this will be environment AND and then final AND module. This is the regular code for the universal shift register. Okay, if you want to have only the shift operation, you don't want to do any rotate left or rotate right, then what we can do? We can change this this opcode. We need not to indicate it as a 2-bit operation. When it is 0, 1 bit will be sufficient. When the value is 0, it is going to do a shift left. When the value is 2, it is going to do the shift right in that way. And you want to do only 4-bit shift operation. Then this value is instead of indicating this 0 to 7, it will be described as 0 to 3. Likewise, based on other requirement, we can write. If you want to do some more operations also, we can do it. If you want to do the shift in the labels, the lower labels has to come to the upper level and upper level has to come to the lower level. Likewise, you can write this portion, you can do whatever you want to do one particular function. That functionality can be incorporated in the code. Now we will see a RTL schematic and the distance waveform for this universal shift register. So this is our RTL schematic. So what are the inputs we used? Our basic input and shift value, clock and reset and the final output. The output is going to be the same individually. Okay, so for our convenience, I have taken this block of code here to explain the diagram. So this is our main, within the case statement row we had it. Okay, now let me explain. This marker is here. We all know that when the marker is there, that value will be displayed here. So the all inputs and the outputs are displayed. So this is my input. So this is my input and this is my output. Okay. Now we see when we gave the input is 0, 0 and when the input is here and it is going to do a left shift, therefore this one has moved here. Therefore the output is 0, 0, 1, 0. This one is shifted out. Okay. And when the input is like this, when we set the input is like this and 0, 1. That means 0 means shift right. Therefore, 0 is entered, this is our input, therefore 0 is entering and this 0 is moved there. And then when this 1, 0 and the input was here, we gave the input like this in this IDS platform. Because when it is here 1, 0, it is going to be our rotate left. So rotate left means what will happen? All the values will be moved and this MSB bit is wrapped around and it is coming here. Therefore, you have this double one. And then when it is 1, 1, that is the thing actually displayed there. Okay, here is the value, this is displayed. So when it is 1, 1 and this is an input, by that time what happens? Rotate right. Therefore, this one as this is shifted and this one is moved here. Therefore, it is the way you can got an input. So likewise, you can create a very long code for this shift operations and we can incorporate many operations in it as I told earlier.